This will be the first in an ongoing series of webinars, so thank you for being our guinea pigs as we embark on this, and thanks for joining us. The webinar is being recorded, so feel free to email us afterward for a shareable link, or we will also have the link on our website, precisioncancer.org. As a reminder, there will be a question and answer period after Dr. Nadald's presentation. To avoid any background sounds, may we ask that you please mute your phones until the question and answer period. If you need to accept another call, please feel free to hang up and call back. We've learned that if you put us on hold, we may enjoy your lovely hold music. Thank you again for joining the webinar, How to Implement Precision Medicine into Your Oncology Practice. Allow me to introduce our presenter, Dr. Lincoln Nadald, MD, PhD. He is the Medical Director of Cancer Genomics at Intermountain Healthcare, an integrated healthcare system located in the Intermountain West. Dr. Nadald completed clinical training in medical oncology at Stanford University School of Medicine, where he is still a part of the research faculty, focusing on cancer genomics and personalized cancer medicine. Dr. Nadald oversees the clinical implementation of genomic cancer medicine across Intermountain Healthcare's 22 hospitals and 180 physician clinics. In his spare time, Dr. Nadald enjoys attending his children's sporting events, water sports, fishing, and athletics. Intermountain Precision Genomics is pleased to present Dr. Lincoln Nadald.
Thanks, Bonnie. Appreciate that. And I really liked the part about the things that I do in spare time and wondered if I could go do some of those now. I'm kidding. Anyway, welcome to everyone who's joining us. I'm hoping this will be useful and informative, and I have some slides that I think can guide the conversation. And if there are questions, feel free to offer those questions. You can write them down. I believe there's a way to do that on WebEx, and at the end of the presentation, we'll have some time for questions as well, and that might be the best time. Today, we're going to be talking about precision medicine and how to implement it into the practice of oncology. This is an evolving field with lots of new things arising and changes occurring every day. And so I thought I would start by sharing a little bit about the complexities of genomics. And really, I think these complexities are what challenge us as practicing oncologists, as providers treating patients, understanding how to, on the one hand, understand the complexities of genomics, and on the other hand, try to provide treatment options for patients based on those genomics. I'll share a little bit about the Intermountain Healthcare Precision Medicine Program and discuss some of the barriers to precision medicine and then how to overcome some of those barriers, at least from the perspective of how we've done it at Intermountain. So, this slide really highlights what is the underlying premise behind precision cancer medicine. So on the left-hand side of the screen, we have a cancer cell, and we can extract DNA, perform sophisticated genomic analysis, and this is available through various clinical lab tests out there in the market. And at the end of the day, what we find are a list of alterations. Patients have anywhere from one to many alterations, some of which are actionable, some of which are not. But those that are actionable typically have drugs that can target them. And the concept becomes, let's find the list of genomic alterations, and then we'll line up the appropriate drug, and we'll see how patients do. And from a population standpoint, this is a graphic that I've borrowed from MD Anderson, but we, in the past, have approached cancer patients as something of a homogeneous population. So we'll see, 10 years ago, we saw all lung cancer patients as the same. We now recognize, with the advent of molecular profiling and next-generation sequencing, that, in fact, the previous homogeneous population is quite heterogeneous, and each patient has their own distinct molecular signature, Each tumor has its own distinct makeup of genomic alterations that has driven that tumor. And if we can understand what some of how that population looks from a genomic standpoint, then maybe we can start to treat them in a more personalized way. And that's the idea behind precision cancer medicine. Well, that sounds great. However, there are some realities that complicate this approach. And it has to do with the number of alterations that we find in any given tumor. This graphic illustrates the number of alterations that we might find in some childhood cancers where there can be up to a dozen mutations, for example, in a neuroblastoma or in an ALL. In contrast, or in comparison, in adults, the number of alterations can be much, much higher. In non-small cell lung cancer, for example, we might find up to 150, whereas in AML, it looks more like a childhood ALL. So the number of mutations can actually be quite high that we find in any given tumor. This is complicated by the report from Gerlinger et al. In the New England Journal of Medicine a few years ago, where they took some renal cell carcinomas and they took the primary tumor and performed biopsies at different sites and then conducted next-generation sequencing on biopsies from these different sites within the same tumor and reported variations and differences in the genomic makeup. So a biopsy from one site may have a list of 5 different alterations, and a biopsy from a different site within the same tumor may have a different set of alterations. And then further, they took not only different biopsies from within the same primary tumor, but then took biopsies from different metastatic sites and discovered that, in fact, there are different alterations between a primary tumor and a metastatic site, and there are even variances between within the same metastatic site. So this concept of tumor heterogeneity is a reality, and it raises the question about how feasible is it to find a set of alterations in someone's tumor, and then from a clinical standpoint, provide treatment targeting a single alteration, knowing that within different metastatic sites there are likely to be different alterations, and even within the same tumor there are likely to be different alterations. And then one additional layer of complexity that goes beyond tumor heterogeneity is this concept of tumor evolution. So if we take a lung tumor, for example, we may find that there are 3 or 4 different clonal populations within that particular tumor. And when we apply an outside pressure, in this case in the form of systemic therapy, then we select for a particular population and really a resistant clone. And what ultimately can occur is that we have one list of alterations that we find in a primary tumor, and then as we apply treatment, we kill off essentially all of the other clones except for one resistant clone. Over time, and as treatment is stopped, or as that resistant clone is able to grow even in the presence of treatment, then additional genomic alterations are acquired, and we now essentially have a genetically new tumor compared to the original starting material. And so this concept of tumor evolution combined with tumor heterogeneity really makes the practice of precision cancer medicine difficult, or at least it would feel that way. And so the question becomes, what do we do? Should we just ignore those complexities? And this is something that I think both scientists and clinicians alike have grappled with and struggled with. And while there's no clear answer, the current state of the art is to, and we're seeing this in a lot of emerging clinical trials, is to identify an alteration from a single biopsy site, provide a targeted therapy in a single agent form, and then monitor the outcome. And for the time being, the answer really is yes. Let's set aside some of these scientific complexities and just ask the basic question of whether applying targeted therapy to patients with genomic alterations improves outcomes or not. And so that is the approach that we initially took at Intermountain Healthcare, and this might be the approach that others choose to take, or maybe will borrow some concepts from this and apply their own concepts. But for the next few minutes, I'll share, at the very least, how we have done it at Intermountain Healthcare. For those who may not be familiar, Intermountain is an integrated health delivery system headquartered in Salt Lake City, Utah, but spread out across the Intermountain West with 22 hospitals and approximately 180 physician clinics. It's an open system in the sense that patients don't have to have Intermountain insurance to be seen and treated at Intermountain facilities by Intermountain physicians. At the same time, physicians do not have to be employed by Intermountain Healthcare. There are affiliated physicians and private practice physicians who see and practice at Intermountain facilities. We see approximately 6,000 new cancer diagnoses per year throughout the system, which gives you some way of comparing to your own system, wherever that may be. When we initially began implementing our precision medicine program for cancer patients a couple of years ago, this is the workflow that we set up. Patients were initially referred to our personalized medicine clinic. Information and education was provided to those patients, including what is genomics and what genomics is not, so that their expectations were managed appropriately. We then went about obtaining an historical biopsy that patient may have had previously from whatever pathology lab was holding the sample. We then went about the sample preparation and wet lab sequencing process that we built in-house. We have been conducting molecular analysis and analytics in-house, and ultimately our workflow includes a molecular tumor board interpretation, and the final step in this whole process has been delivery of treatment. And our initial feeling has been, if we're going to perform this kind of testing and do a genomic analysis looking for targeted treatment options, then we ought to be concluding with actually delivering the targeted treatment. Otherwise, it's kind of a wasted exercise if we're not going to actually offer patients treatment. The initial question we had at the conclusion of our initial pilot study was whether this type of testing had an impact on management. So our pilot study consisted of about 200 patients who all received genomic testing, and then we looked to see whether the referring oncologist changed management and whether that patient had any changes in their overall treatment course. And it turns out about 75% or so, almost 80% of patients had change in management of their care, either immediately or subsequently down the road. And so there was evidence that this type of testing was associated with clinical utility. At the very least, providers were using it to guide management and to change treatment for patients. These patients, we know, at least in our pilot project, have been essentially the sicker patients. These are advanced patients with advanced disease. They're all metastatic patients who have failed standard therapy, and they have refractory disease and are essentially out of options. We conducted a cohort study to ask the question of whether the change in management that we saw produced any improvement in results. Were there any improvements in outcomes? And this is on the screen here, a diagram of what that study looked like. We took the first 200 patients and found that about 80% or so had actionable mutations. There's a bit of a debate about how to define an actionable mutation. We defined it as a mutation that has been validated in the literature, that we know is a clinically relevant variant for which there is a drug. And about 80% of patients in our cohort harbored an actionable mutation in their tumor. About half of those went on to receive targeted therapy in various forms on clinical trials or in an off-label fashion or in various ways. They received a targeted treatment. And we asked the question whether this cohort of patients could be matched to patients within our same institution who had received standard therapies, a third or fourth line chemotherapy, for example. And so we conducted this analysis and were able to find 36 patients who had received this precision medicine approach and matched them according to diagnosis, age, gender, and number of previous treatment lines to 36 patients who had received some kind of standard chemotherapy or other therapy. This number of previous treatments was our attempt to control for the disease progression, the stage of progression for these patients. And they were very tightly matched in terms of all the other characteristics, age, gender, diagnosis, and so forth. The punchline from that analysis, and this has been submitted for publication, is that a progression-free survival analysis revealed that those patients who received traditional treatments had a PFS of about 12 weeks, which is consistent with previous clinical trials, phase 1 and some phase 2 trials, where patients with advanced refractory disease just don't survive that long on third or fourth or fifth line treatment. In comparison, those patients in the targeted treatment cohort had a progression-free survival that was nearly double, with a significant p-value. The Kaplan-Meier curves looked like this, so there was some separation in these refractory patients, which was interesting. None of us anticipated seeing that big of a difference, so that was encouraging. A major question that we had was regarding the cost of care. Those patients who received standard therapy had a cost around $5,000 per week of progression-free survival. By way of comparison, those patients who received a precision medicine approach using genomics had a cost of care that was very similar. From a statistical standpoint, those costs were not distinguishable. They appeared to be the same. If we looked at the overall cost of care, because those patients in the precision medicine arm had a progression-free survival that was nearly double those in the standard arm, the overall cost of care was higher in the precision medicine arm than in the standard arm. But when normalized to progression-free weeks, the cost of care was the same, leading to the conclusion that using genomic targeted therapies can improve progression-free survival without increasing the cost per week of life. So that's how we have attempted to approach precision medicine and establish it, and I have alluded to this pilot project, and we learned some important things during this pilot project. We learned some of the barriers that exist, and those who are joining us by WebEx today may have experienced some of these same barriers, and I want to take a few minutes now and talk about what some of these barriers are and how we have gone about trying to overcome them. And I know there are lots of others on the phone who have faced similar barriers and overcome them in other ways, and it's great to hear all of those. One of the major barriers that we faced initially was testing, where to get the testing done. We discovered there are lots of commercial labs out there that are offering this type of testing, for-profit labs whose they have different characteristics in the lab testing, and it can be difficult to wade through that. Some labs will just test a handful of genes and don't necessarily make it clear that not only are they only testing a handful of genes, but they're only checking a few distinct locations within those genes, so-called hotspot testing. So they may just be checking codon 12 and 13 in KRAS and ignoring everything else, and only looking at a few dozen genes in a not very comprehensive manner. Contrastingly, there are other tests out there that will that will test hundreds and hundreds of genes, the majority of which really don't have treatment options available. So, and we've, upon further investigation, it looks like in some cases those companies are really more focused on partnerships with pharmaceutical companies, and they're essentially conducting research to identify the next list of treatment of targets for those pharmaceutical partners. And so when a test is ordered, they will sequence 500 or 1,000 genes, knowing that only maybe 80 to 100 of those genes are really actionable. So there are lots of barriers out there, and the way that we frankly have overcome this is by implementing our own testing and building our own service to run our pilot project, and we have now begun to offer that externally, and I'll talk about that in a minute. A second barrier, of course, is interpretation of the test results. This is a big challenge. Sometimes getting this list of alterations back can read like Greek, and I'll talk about that in a minute. And then finally, procuring drugs for patients, if there is an actionable mutation, is a whole separate endeavor that deserves some comments. So just first about the testing, we, I mentioned, set up our own testing in-house. We have partnered with some others, including a company called Toma, to help power this. This portal that we've worked with SciOps to develop this electronic online portal through which our own physicians are ordering our genomic testing, and we now are offering this to any provider in the country that wants to have their patient's tumor tested, a genomic analysis conducted. It's available through precisioncancer.org. Intermountain Healthcare is a nonprofit organization, and so this is a .org effort. The primary interest here is not a big money-making effort like many of these for-profit commercial labs. Rather, it's a data generation effort, and we have found that it took a lot of work to overcome some of these testing hurdles, and the interpretation challenge can be overcome by generating increasingly more data. And so as we offer this test to more and more of our colleagues and partners, we can generate more data, learn more rapidly, and at the end of the day, we think that it's patients that benefit. Some of the clinical test requirements that we've discovered are important is to test the entire gene. KRAS is the example I used before. There are mutations in KRAS that go beyond codons 12 and 13. Codon 61, for example, can harbor activating mutations. Not only that, but there are truncating events that can happen in other important tumor suppressors that are missed if a testing service only looks at certain portions of the gene. So we think it's important, whatever testing service someone uses, they ought to make sure that that test is covering the entire gene from end to end. Detecting copy number alterations is critical. The literature supports that about 1/3 of all actionable mutations are copy number alterations, in other words, amplifications. So some testings, in fact, the majority of testing services don't report on copy number alterations, and so we have found to be wary of those, and frankly, it might be worth avoiding testing services that don't report copy number alterations, because you'll be essentially exhausting your patient's tissue sample and getting incomplete information. Finally, it's important to use a testing service that is highly sensitive because it will yield more treatment options. So if you have a testing service that has a very high coverage of the various genes, then you have a better chance of identifying an actionable mutation. In addition, you can avoid the dreaded quantity not sufficient determination. So I'm guessing there are lots of people on the phone who have run into this problem where a genomic test is ordered, and then a few weeks later you receive a notification that there was insufficient material in your patient's sample. and the test couldn't be completed. And so trying to sift through the various testing services to make sure that you're selecting one that gives your patient the best chance of finding an actionable mutation and avoiding the dreaded quantity not sufficient is worth the extra time that it may take. So what are some of the barriers to personalized medicine? Well, we've overcome the testing thing by implementing our own testing service. We call it ICG100. Anybody can use this. Please feel free to if you would like. The second barrier, interpretation, is a big challenge. So we've overcome this by implementing a molecular tumor board. There's been lots of discussion nationally about this. People are talking about it at some of the national meetings. At ASCO recently, there was a lot of conversation. At the upcoming AMP, the molecular pathology meeting in Austin, Texas, there will be a session dedicated to talking about molecular tumor boards. We've established a molecular tumor board. Other institutions have one as well. These can be very, very helpful in evaluating the list of variants in a patient's tumor. The molecular tumor board that Intermountain Healthcare has established is multi-institutional in nature, so it's hosted and anchored by Intermountain Healthcare. It's an open tumor board, so any provider from anywhere in the country can call in and participate and just listen if they like, or they can even share cases and get feedback on cases. It's comprised of experts in cancer genomics from organizations across the country, including from Stanford University, the University of Oklahoma. We've had participants from the Swedish Cancer Institute and Stanford Healthcare and ProMedica and Thomas Jefferson University, and on the list goes. The power in a molecular tumor board that I know many have experienced in standard tumor boards is in coming to a consensus. And so we're able to evaluate a list of variants from a patient and use the tumor board's experience with genomics, not only clinically but scientifically, and ultimately come up with a consensus interpretation about which mutations should be targeted and with which drug. At Intermountain, we actually have taken a step beyond what we have seen available in the market, and we've included the molecular tumor board interpretation on the report itself. What's showing here is an example of this ICG100 test that I alluded to before that we've been using internally. This report includes at the very top, the very first thing that is seen is this molecular tumor board interpretation. So here are the variants, for example, that were identified in this patient's tumor, both a PI3 kinase mutation and a HER2 amplification, or ERBB2. So, of course, HER2 amplifications are well characterized, well studied, many treatment options in breast cancer, but here this patient has a melanoma. So how are we supposed to understand and rationalize that? Well, the molecular tumor board was very helpful in this particular case for that exact reason, and the question was, what should be targeted first, the HER2 amplification or the PI3 kinase mutation? And turns out in this particular case, there was lots of discussion around the scientists' and clinicians' previous experience in trying to target PI3 kinase mutations, and really the lack of robust response in doing that. There just really hasn't been lots of good outcomes when targeting PI3 kinase mutations with mTOR inhibitors. And in contrast, targeting HER2 amplifications in diverse tumor types outside of breast cancer has been useful. And we've seen that not only in breast cancer, but also in other types of cancers, including bladder cancers and endometrial cancers. And so utilizing targeted treatments against HER2 in a melanoma for a patient that doesn't have any other options and has exhausted the standard of care might be an approach that could yield a response. The list of variants that we find is sometimes long and can look like this. And so, 2 different APC mutations, a CDK5 and CDK8 amplification, FLT3 amplification, P53 mutation, and the list can be longer. I know there are people on the phone have seen even more mutations, and it can be overwhelming at times. And so trying to wade through not only the number of different genes, but also all of the different variants, which can can be difficult is really one of the benefits of having a molecular tumor board, so that this can be distilled down into a single rational interpretation that just includes a gene and a drug. At least that's how we've tried to approach it. Having access to some of the more in-depth literature can be helpful. Some providers are really interested in reading more. Other times, we don't have the amount of time required to dive in that deeply. In the portal that I showed, all of these variants are hyperlinked, so that if a practitioner had time and interest, they could click on a hyperlink, for example, and read more about the HER2 amplification, and up would pop this little window. And we have found this to be very useful. We employ this quite frequently, and so we can read about HER2 and activation of HER2, and we can even hyperlink out to the primary literature if we want, and then we use these additional tabs at times to understand more about a particular alteration in disease. We can learn about what is FDA approved in various indications. We can learn about the incidence of this particular alteration in different tumor types. We can see information about phase 1, phase 2, and phase 3 data, preclinical data, and so on. And so this is all information, and we partner with some outside groups, including NF1, to help populate this. And we've made this available in our portal so that practitioners can read more and learn more about genomic alterations. There are always a list of these variants of unknown significance, and trying to know how to handle these is always a challenge. Again, that's where our tumor board has proven to be helpful. Generally, we don't ever act on, and I haven't seen the molecular tumor board ever settle on acting on a variant of unknown significance. By definition, we don't really know what these alterations mean. In many cases, they're simple SNPs. They're just simple normal variants. Occasionally, they can represent an alteration that we didn't know about. There are some clinical trials that will allow patients to enroll based on a variant in a gene, whether its significance is known or not. An example is the signature series of clinical trials from Novartis, where patients can enroll and qualify for a trial whether their variant is validated and known or not. And so VUSs were allowed, for example, on the signature series of clinical trials. So we always like to include these and look at these just to make sure that we understand everything that's going on. Sometimes the number of variants of uncertain clinical significance can give insight into genomic instability and mismatch repair problems. Evaluating the clinical trials available for a patient is a step that we take for each patient and is always considered by the molecular tumor board. This list of clinical trials is actually available, and our providers can access it through that portal that I was pointing out previously. And so for a patient that has a PI3 kinase mutation, for example, you can read about some of the clinical trials that are available, including the contact information and how to enroll a patient there, as well as the locations for where that trial is available and open. And so considering the clinical trial options for each patient is a critical step. And so all of this we have tried to incorporate and make available for providers by including it all in one location. Not only is it available on the report, but also in the portal, and including the molecular tumor board interpretation, the variants, the clinical trials, the variants of uncertain significance. All of that can be accessed. And we have found that when implementing genomics for patients clinically, that considering each one of these aspects is important. So that's how we've overcome those first two barriers, both the testing part and the interpretation part. And then finally, there's this drug procurement challenge, how to go about obtaining drug for patients. Well, we've done this in a variety of ways. There are people across the country who have done it in a variety of ways. Clinical trials is always a terrific option and really our first choice. This can be done through lots of the basket trials that are opening up. So these are trials that patients can qualify for based on the strength of genomic alteration, regardless of tumor type. An example is the MATCH trial that is opening at many locations today, as a matter of fact. The MyPathway trial from Genentech is a trial that utilizes some of the Genentech drugs such as vemurafenib, trastuzumab, vismodegib, the hedgehog inhibitor, and some others. The Signature series of trials from Novartis is one that patients could qualify for, and they could get an FGFR inhibitor regardless of tumor type, or a PI3 kinase inhibitor, or a CDK inhibitor, and so forth. So that's one option. Sometimes targeted therapies are available in an on-label fashion. Of course, that's terrific when that occurs. And sometimes they're only available off-label. We have gone to the length of making this available to our providers by having a drug procurement option available right in the portal, so that as a provider is in there reading about an interpretation, they could actually click on the name of a drug, and up would pop this order form. In this case, Afinitor, and you could put in the dose that you like and push confirm and order. And then we actually have a dedicated team who will go about working with the patient's insurance to obtain the therapy for that patient. In the remaining few minutes, I just wanted to share some examples of cases that we have seen that highlight some of the positive outcomes that can occur with genomic medicine and targeted therapies. This is a case of an elderly gentleman with lung cancer, squamous cell carcinoma, who had progressed through several lines of chemotherapy. This patient, we performed a genomic analysis and found this FGFR1 amplification. This was before the PD-1 inhibitors were available. This patient went on to receive pazopanib, actually, as an FGFR inhibitor. And here was his primary mass. He had metastatic lesions elsewhere. But over time, we started to see a cavitation of that primary mass, which was very interesting. He ended up staying on that drug for about 18 months, did extraordinarily well, and has recently gone off the drug due to fatigue and some other side effects, but continues to have stable disease for almost 2 years now. The thing we like to joke about with him is he's 79 years old and came into clinic one day, and we asked him how he's doing, and he said, "Well, I'm feeling very optimistic about life." And we said, "That's great." And he said, "Yes, I'm feeling so optimistic, as a matter of fact, that I got married last week." And so we were happy to see that he's continuing to live his life as much as possible. This is a melanoma patient who had progressed through ipilimumab and actually was BRAF wild type. The PD-1 inhibitors weren't yet available. She had a c-KIT alteration. And c-KIT can be targeted with imatinib. She got imatinib, and this primary mass that measured about 8 centimeters just near the right adrenal gland shrunk down to about 2 centimeters over a matter of months. She felt extremely well, as most patients do when they're enjoying a response. She stayed on that drug for about a year, which is terrific in melanoma. Ultimately, the disease progressed through, and she transitioned to other treatments, but nevertheless had about a year's worth of response. This is another lung cancer patient in mid-50s who had progressed through standard chemotherapies, including a platinum doublet. His tumor harbored a BRAF mutation. It was not the V600E that we're familiar with from melanoma and can occur in some other tumor types. It was another BRAF mutation. This patient was able to get a MEK inhibitor in the form of trametinib, and had bulky disease here in the mediastinum and hilum, as well as in the right supraclavicular region. After several months on this targeted therapy, he had a dramatic response. He felt really well, gained a bunch of his weight back, did well for about 15 months before his disease ultimately progressed. And we actually repeated the genomic analysis and were able to get him on a different treatment option. So in summary, cancer genomics and precision medicine is complex, there's no doubt about it, but treatments can be effective nevertheless, even in the face of these principles of tumor heterogeneity and tumor evolution, not only can treatments be effective, but actually the principles of heterogeneity and evolution represent additional therapeutic options. So we have found when patients progress on one targeted therapy, after a year or so, an additional biopsy can be obtained, and often we'll find a new actionable alteration wasn't there before, and that represents another treatment option. Our own pilot study revealed that we can see an improvement in progression-free survival without increasing costs, which is important. Payers are very interested in this data, and this will be elucidated in a forthcoming manuscript. Some of the barriers to clinical implementation can be overcome. We think a molecular tumor board is an important part of that. Having a molecular tumor board interpretation right on a genomic results report, we have found to be extraordinarily helpful, because you can go back and refer to that over and over again, knowing that a live molecular tumor board evaluated it, included it on the report. And then finally, drug procurement is an important step that's not necessarily easy, but is getting easier. We're doing it through that same portal that I mentioned. Others have other ways of doing it. And we have found that we're having an easier and easier time with getting drugs approved, and we're also finding that the clinical trial options are improving significantly for patients. So with that, I will pause and thank everyone for their time, and I'd be happy to take any questions.
Do we have any questions? There's a raise your hand option, I think, on the WebEx, but we're open to take any questions now. Must have covered everything beautifully.
It's all crystal clear, obviously.
Exactly. All right. Well, one last chance. If anyone has any questions, comments, challenges. Okay. I don't see any hands up or input.
Well, they can contact us by email or any other way if questions come to mind later.
Yes, our website is precisioncancer.org, so feel free to log on, and there's a Contact Us button, and the website also has the portal that you can use for ordering the test and receive more information as you click around about the test. So thank you for joining us, and we look forward to next time.